Hi everyone, so let's see the implementation for the problem rotated search. So let's go through the logic that we have just discussed. So in the first step, I have created this function rotated search that takes input the vector and the key, and here n gives me the size of the vector. So as I discussed, we will build a modified binary search here. So I take a start that is at 0, I take a end that is at n minus 1, and we have the same uh, while loop that we use in binary search. And we will do one more thing here. We will break our logic into two cases as I discussed. Okay, so first we need to compute the midpoint, so s plus e by 2, and then we need to check whether array of mid equals key. Okay, so if this is the simplest case, if you find the element at the mid, you simply return the midpoint. Otherwise you have two cases: the mid lies on the left line or the mid lies on the right side. So if array of start is less than equal to array of mid, this is basically the case when we are on the left side. Okay, and otherwise if I put a else here, we are on the right hand side. Okay, so right of the pivot. Okay, so if you want a quick recap, so this is what I said. If mid lies here, okay, then you can say that array of start would be less than mid. But if mid lies here, in this case array of start would be greater than mid. Okay, so in that case we will enter this case. Otherwise, for the first case, we will have our logic will be written in this case. Okay, so here also we will have two more cases. We have to check whether the element lies on this part or on this part. So this is part 2, this is part 1. Okay, this is what we need to see. So for this part, let's try to write the logic here. So we can check if key is greater than equal to array of start and key is less than equal to array of mid. Because this line is sorted, you can make a comparison to check. Okay, so let me just repeat again. Now we have divided our problem into two parts about the mid. Okay, so this is part 2. This green line denotes part 2. The green line is not sorted, but this dashed line, this is sorted. So that's why I'm checking if key lies between a of s and a of mid. So if it lies in this part, then we simply reduce our problem to this part. We will bring our end from here to here. The end will come to mid minus 1. So let us do this thing. So we can say in this case end will come to mid minus 1. So if this is not the case, if the key lies outside this dashed part, in that case I can say, okay, my start will go to mid plus 1. So I can say s equals mid plus 1. So this completes our first case when the mid lies on the left part. Okay, so in that case start will go here. Now let us see the complementary case. In the complementary case, what you will have is you will have something like this: mid lies here, and now you can check whether the element lies on this line. Okay, if it lies between mid and end, then you can search here. Otherwise you can search in this part. You can search in this part. So let us see. So we can say if key is greater than equal to array of mid and key is less than equal to array of end, then start equals mid plus 1, else we can say end equals mid minus 1. Now some of you may ask why we are making comparison with respect to this line. Why are we not saying, okay, if key lies between start and mid? The answer is this start and mid line is not a sorted line. It has a break in between, so we cannot make a direct comparison. But here the search space is monotonic. We can make a comparison between array of mid and array of end. We can check if key lies between these 2 points, then you search in this part. Otherwise you search in this part. Okay, so this is the complete logic. And once the while loop stops, you will have the midpoint, And if we come out of the while loop, that means we could not find our answer. We can say return -1. So I think that's all. And now what we can do, we can try to build our code and we can run through it. And let me show you. Okay, so let me run this code and let me search for the element, let's say 5 and 4. So 5 is at 1, which is fine. About 4, 4 is at index 0, which is also fine. Let me search for 2 and 3. So it is at the last. 2 is at 6 and 3 should be at 7, which is fine. And maybe let us search for 0 also. 0, 1, 2, 3, 4. The answer should be 4. Sorry, let me search for 0. The answer should be 4, which is fine, right? So you can see this algorithm that we implemented is working fine for all cases. And that's all. I hope you really understood this.